Hello, grade 12 chemistry students. This is a video talk through on Le Chatelier's principle and the practice questions for Le Chatelier's principle. Le Chatelier's principle is an important one for the understanding of equilibrium. It, in summary, is the idea that when an equilibrium is disrupted or disturbed, and that can happen in a number of ways, the equilibrium will shift to counteract, or you could think of it as cancel out that shift or that disturbance and re-establish equilibrium. The equilibrium will be a new equilibrium, but the disturbance will always be counteracted. So using Le Chatelier's principle is a way that chemists can exert some control over a reaction and get the maximum amount of whatever substance they so desire. So if you want more product or more reactant, you either adjust concentration or temperature or the volume of the container in order to maximize the product made. So let's look at some examples of how Le Chatelier's principle is used and what shifts can happen and how the reaction will counteract those shifts. So let's have at it. So for number one, we have a reaction where hydrogen gas and iodine gas combine to form hydrogen iodide, which is also a gas. So on letter A, we are asked to predict the shift when in equilibrium when more HI gas, so that's more product, is added to the system, and to explain. So just let me get my text box in here. So adding a product. So HI is considered a product. Now, I know that can be not, when we're talking about equilibrium, there's really a blurry line between what are reactants and what are products. But the right side of the arrow is still considered the products, and the left side is still considered the reactants. Although there's going to always be some of each in a system that maintains an equilibrium. So we're going to say adding a product, which is on the right side of the arrow, will cause the equilibrium to shift left, which is towards the reactants. This is because adding more product, more HI, increases the concentration of HI. There are now more HI molecules that are able to collide with each other, and that will increase the rate of the reverse reaction. So having more HI, so if we just draw a few dots here, I'm gonna do this. We're gonna say that the black dots are hydrogen and the red dots are iodine and the yellowish dots are HI. So if we have this sort of setup, and I'm going to draw twice as many dots of HI based on the stoichiometry. Let's say we double the concentration of HI. Okay, now you can see there are just more, and this is going to be a gas, so it's going to be in a container, and this is also in a container. This is all happening in a container. These molecules are all mixed together. I've separated them for the sake of example. Now there are going to be more collisions between product or HI molecules. And what that will do is it will increase the rate of the reaction that goes back to I2 and H2. So the product molecules are reacting more and turning back into HI, which will have the effect of increasing the concentration of the reactant molecules as equilibrium shifts. So in general, whenever you add a product, that's going to cause the reaction to shift left or towards the reactants. Letter B is the opposite idea. For letter B, these text boxes don't work super well. We are asked to what will happen if we increase the concentration of I2. Well, increasing the concentration of I2, which is adding a reactant, will cause the equilibrium to shift right towards the products. And the reasoning is exactly the same as I just explained. Now we have more I2 molecules over there. There are more of them that are going to be able to react with the H2 molecules, and that will have the effect of pushing this equilibrium to the right, resulting in more HI molecules being formed. Let's move on into number 2. So we are told for the reaction below, predict the direction the equilibrium will shift given the following changes. So there's 4 changes that are happening in this particular reaction we're asked to explain. We are told that the temperature and the volume are held constant. So this is just going to be changes in concentration. So the addition of ammonia, which is a product in this case, so adding a product causes the equilibrium to shift towards the reactants. So that could also be called a left shift. It increases the rate of the reverse direction. So increased rate of reverse reaction. The removal of nitrogen dioxide. So nitrogen dioxide is a reactant. So removing reactant causes the equilibrium to shift left. So remember, we're counteracting what the disturbance has been. So if we have decreased that concentration, the reaction will shift to make more of it. The reaction will shift left to create more reactant. So the idea here would be that we have decreased the rate of the forward reaction by removing some of the reactant. So now the reverse reaction has a greater rate than the forward reaction, and the result will be more reactant being formed. So again, that's a right shift. The removal of water vapor. So we've decreased the concentration of water. So what that would do is it'll decrease the rate of the reverse reaction, and we'll have the opposite effect that we saw in letter B. This will cause a left shift. No, I'm sorry. that will cause a right shift. What am I thinking here? A right shift. You guys, I just realized I said the wrong thing on letter B. My apologies. This should have said left shift. Removing a reactant causes the equilibrium to shift to the left, so that will be a left shift. Addition of hydrogen. So if we increase the concentration of hydrogen, that will increase the rate of the forward reaction. And that will be a right shift, making more products. Okay, let's move on to number 3. So we are told here that the pressure on each of the following systems is increased. So by decreasing the volume. So remember, if we decrease the volume, that will lead to an increase in pressure. If we have a container like this that has, let's just say, 5 or 6 molecules of gas in it, it's going to have some pressure. But if we make that container smaller, there are still going to be the same number of gas molecules in there, but now they will be hitting the walls of the container more frequently, and that will cause an increase in pressure. So we decrease the volume by increasing, we increase the pressure by decreasing the volume. So what happens when we do that? The thing to look at is how many molecules or moles, whatever you're thinking of here, how much, what quantity of gas is on each side of the equilibrium arrow. So on this side, we have 3 molecules of gas, and on this side, we have 2 molecules of gas. So increasing the pressure can be counteracted by decreasing the number of gas molecules. The less gas that there is in the system, the less pressure that will happen. The pressure will be reduced. So if we increase the pressure, we're going to cause the reaction to shift right, which is towards less molecules of gas. So this reaction will shift to make more products. There are less molecules of gas on the product side versus the reactant side, and it'll shift towards less products. Okay, so on letter B, there are 2 molecules of gas on this side and 2 molecules of gas on the right side. So this will have no change. Changing the volume of this container will have no effect. There are the same amount of gas on each side. So no effect. Letter C, this is a solid, so there's no gas there. We have 1 molecule of gas on this side, so increasing the pressure is going to cause this reaction to shift towards where there's less gas, so this will have a left shift towards the reactants where there is less gas. Okay, and for letter D, we have no molecules of gas and no molecules of gas, so this will also have no change. If there's no gas present in a system, changing the pressure is not going to have an effect on the equilibrium. Okay, let's look at number 4. Here we are given a reaction, and we are asked to list 3 ways that the following equilibrium reaction could be forced to shift to the right. So we are looking for how could we make more products. how could we make more products? That's what the right shift means. Okay, so we're not told anything about temperature in this question, so we don't know how temperature changes will affect the equilibrium, but we do know a couple of things. We know that if we add products, oh, my bad, add reactants, that will cause the reaction to shift to the right. So that increases the rate, increased rate of forward reaction. So this will produce more products. The equilibrium wants to counteract. It wants to use up the reactants, and therefore it will make more products. The equilibrium shifts to use up the reactants, therefore more products. Okay, we could remove product. If you remove a product, or products in this case, both of them, one or the other, what that will do is it will decrease the rate of the reverse reaction. And the forward reaction will be have the same rate, and it'll be greater than the reverse reaction, and that will cause the equilibrium to shift right. So the equilibrium shifts to make more products. It's always just counteracting the disturbance. Okay, notice here, if we look at how much gas we have, there are 2 molecules of gas on the reactant side, and there are 3 molecules of gas on the product side. So if we can decrease the volume, which would increase the pressure. Sorry, whoop, I got that backward, you guys. I want to increase the volume, which would decrease the pressure. Because we want to have this equilibrium shift to where there's more pressure. More gas means more pressure. So there are more gas molecules on the product side, and decreasing the pressure will want to counteract by increasing the pressure of the system. The equilibrium shifts to increase the pressure by producing more gas molecules. Okay, so those 3 effects. Let's have a look at number 5. Given the following equilibrium reaction, what will be the effect on the following disturbances? So we have carbon. Notice that that's a solid, and oxygen combining to form carbon monoxide. What will be the effect on the following disturbances? Adding carbon monoxide. So we're told that it's constant volume and temperature. So nothing is changing for the temperature or the volume. So if we add carbon monoxide, that will increase the rate of the reverse reaction. and the equilibrium will shift left. Right? It's going to produce more products. It's going to shift left. If we add O2, so what that will do is it will increase the rate of the forward reaction, and the equilibrium will shift right. Okay, adding solid carbon. So adding a solid is not going to affect the equilibrium here. There's an exception to the rule here. So adding a solid or a liquid, if you remember, we don't include solids or liquids in our equilibrium calculations. So adding those has no effect on the equilibrium because it doesn't change any of the concentration. Adding solid or liquid doesn't change concentrations. So the equilibrium will not shift. Decreasing the volume of the container. So we got to add up the gas molecules on each side. So the left side has one gas molecule, the right side has two gas molecules. And we can see here that decreasing the volume will increase the pressure. So this will cause the reaction to shift left. So that will cause the reaction, the equilibrium will shift left to reduce the pressure. Less gas on the reactants side. So the reaction will shift towards making less gas, which has the effect of reducing the pressure. Okay, number 6 and 7 are dealing now with temperature. So we are told for each of the following equilibria, predict whether the system will shift in the forward or reverse directions, and explain. Note the energy changes involved and assume that the volume remains constant. Okay, so we are told that we have heat removed from a reaction where, let me just rewrite this a little bit better. A plus heat is in equilibrium with B. Notice how I wrote heat as a reactant in this case on the left-hand side, because we are told that this is an endothermic reaction. It has a positive enthalpy and positive delta H. Remember that positive delta H's are endothermic reactions. We did a whole bunch of these kind of things. So that would be a positive reaction. Positive enthalpy, in this reaction, it would be endothermic. So think of heat as either being a reactant if it's endothermic or a product if it's exothermic. So if we remove heat from this system, that's like we have removed a product. So removing a product will cause this reaction to shift left, right? Less heat is like removing reactant. I'm sorry, I think I said product in my last statement there. That should be removing a reactant. Less heat is like removing a reactant. So the equilibrium will shift left to produce more heat. It shifts to where the heat is created if the disturbance is removing the heat. Okay, so I don't know why it says heat here twice. It should just be heat. Heat is removed, so here we have A plus B gives us 2C plus heat, and this is an exothermic reaction. Heat is a product of this reaction, so if we're removing a product, the reaction will shift right to produce more heat. So equilibrium will shift right to produce more heat. And on C, we are told that heat is added. So this being exothermic again, I would write in here that heat is a product. And if we increase the heat, we have added more product. So the equilibrium will shift left to use up that product. Equilibrium will shift left to use up the additional heat. Okay, so to answer the question fully for each of the following equilibrium, predict whether the system will shift in the forward or reverse directions. If it's shifting left, that will be in the reverse direction. If it is shifting right, that'll be in the forward direction. And if it is shifting left, that will be in the reverse direction. All right, let's finish off this set of practice questions with number 7. In each of the following equilibria, would you increase or decrease the temperature to force the reaction in the forward direction? And explain. So this reaction is telling us that the delta H is positive. So what that means is that heat is a reactant. This is an endothermic reaction. That says that kind of looks like feet. That should be plus heat. Plus heat. So if we increase or decrease the temperature, we're going to change the position of the equilibrium. So in order to push this temperature in the forward this reaction in the forward direction, which is to the right, we would want to add more heat. So adding more heat would essentially add more reactant, which will cause the reaction to go further right to use up the heat, away from the heat. So in this case, you'd want to add more heat or increase the temperature of the reaction. Okay, and last one, B. In this case, exothermic as a reaction, we have a negative delta H. So in this case, we'd want to reduce the temperature. So that would push the reaction to produce more heat to counteract the temperature that has been reduced. Okay, thank you very much for your time.